Morning. Hello? Yeah. Good morning. Today, I have the pleasure to introduce our third keynote speaker, Professor Kohei Nakajima. Professor Nakajima is an associate professor at the University of Tokyo. And before joining Tokyo, he has been working at the University of Zurich, ETH Zurich, and Hakubi Center for Advanced Research at Kyoto University, where he was awarded the title of the Hakubi researcher at the Kyoto University. He is an author of several books, including Reservoir Computing and also The Science of Soft Robots. His research includes nonlinear dynamical systems, information theory, physical reservoir computing, and soft robotics. And today he will tell us about physicalizing deep learning. So please welcome Professor Nakajima.
Thank you very much. Thank you very much. I'm Kohei Nakajima from the University of Tokyo. And first of all, thank you very much for inviting me to this exciting conference. I'm honored to be here. And I hope you guys will enjoy my talk today. So the title today is Physical Deep Neural Network Using Natural Dynamics. So basically, I would like to introduce a method to exploit physical natural dynamics for your machine learning purpose or computational purpose. So I would like to start from this video. Okay. Do we need to, is it too bright? It's okay. So as you can see, it's okay. Okay, thank you. Okay, so as some of you may already know, I have been working on this platform for more than 10 years. And I have been constantly arguing that this type of physical body dynamics can be used as a computer. And what does it mean? So there's no, for example, there's no CPU, obviously. There's no random access memory. But I have been constantly saying that this can be used as a computer. And to understand why we can use this dynamics as a computer, we need to understand the concept of reservoir computing and physical reservoir computing. So I would like to start from that point today. Okay. And I think the concept of reservoir computing is has a history. So it started from Herbert Yeager's echo state network and Wolfgang Mass liquid state machine. So it's almost more than 20 years. So many of you already know, but I want to check the main points of this framework. So basically, reservoir computing was proposed as a learning scheme for a recurrent neural network. And as you know, in conventional sense, we use backpropagation through time method to train the recurrent neural network. So by using this backpropagation through time method, you tune all these weights inside the network, and you try to bring entire system, entire network to some target function f. But in the reservoir computing approach, we don't do that. We only tune this readout part. And we prepare huge amount of nonlinear elements randomly coupled each other in the middle layer. And this part is called reservoir, and it forms high-dimensional nonlinear dynamical system. And usually we don't, of course, there are lots of variations recently, but usually we don't tune all these weights inside the reservoir, and also the weights coming from input to the reservoir. And we only adjust this readout part. So as you can see from this system architecture, the philosophy is a bit different compared with the conventional deep learning or these recurrent neural network backpropagation through time methods. So as I said, in the conventional sense, by using BP, you're trying to bring entire system, by tuning all these weights, you're trying to bring entire system to target function F. But in the reservoir computing approach, we increase the complexity of the middle layer part, and then we pick up the important elements at the readout part. So we can, what should I say? We don't destroy these intrinsic dynamics we have in the reservoir part. And obviously, according to this system architecture, the dynamics of the reservoir is very important, especially this nonlinearity in memory included in this reservoir dynamics is very important to characterize the computational capability of this system. And also the important point is that because this reservoir part is not affected by the training, we can replace this middle layer with the physical dynamics. And that's the basic concept of the physical reservoir computing. So left-hand side is the conventional random recurrent neural network, echo state network, the reservoir computer. And just like the conventional echo state network, we inject input to this physical system as a motor. For example, in this case, soft robotic arm, just like we saw in the previous first slide. So just like the conventional reservoir, we inject input as a motor command, and you generate these passive body dynamics, and you monitor this body dynamics by using these embedded sensors. And then you treat these sensory reading as dynamics, internal dynamics, and you adjust this readout part. And then you use this body dynamics for your computation purpose. This is the physical reservoir computing. So you can also put some kind of feedback loop, and you can embed some closed loop control in the body. So interesting point is, usually, for this left-hand side, this one is basically driven inside your PC by using some algorithm, right? But this algorithm is outsourced to the physical dynamics, and we let this physical dynamics compute something, and then we take, by using this sensor, we pick up the result of the computation, and we use that for our computational purpose. That's the concept. So this is the actual example. I won't go into detail for this one today, but so this video is the video that I showed in the first slide. So this one was, so we injected binary input series. That's input. And according to this binary input series, we emulated several Boolean functions. So I won't go into detail, but we have 6 tasks simultaneously running. And we want to emulate several Boolean functions, which requires memory and nonlinearity. And we found that, so this black line is a target output, and red line is a system output. So this one's the input. And according to this input, you generate this body dynamics. And we have this sensory time series. Using this as a reservoir dynamics, we emulated these 6 Boolean functions simultaneously. And you can see that for several Boolean functions, the performance is almost perfect. So somehow, although it has a limitation, we can use these body dynamics as a recurrent neural network. And please check this paper for details. Now, let's check whether this also works for the closed loop control. So just like the previous case, we inject input as a motor command. You generate the passive body dynamics. And then you adjust this readout part. And then this output is, again, fed back as a next motor command. And so, for example, by using this, we can, so in this case, this memory and nonlinearity is only coming from this body dynamics, because we are only adjusting this linear readout part, and this one is static. So, for example, if we want to emulate this kind of oscillatory behavior, like it has some kind of certain duration of time, and then usually to embed this kind of oscillatory behavior, we need a counter. So we have some parameter like tau square here. And if you run this one in the PC, you have some kind of counter and you count tau square. And if tau square passed, then it switched to 1 to 0 or 0 to 1. But we don't have this kind of counter right now. We only have this current body dynamics. And by using this current transient body dynamics, we need to determine, only by this static readout, we need to determine whether it really passed tau square time steps or not by only checking this transient dynamics. That's the challenge here. And this is already a result. So we can successfully embed this kind of closed loop control into this body dynamics. And we also put some kind of manual perturbation, because right now this one is, this body is also acting like a brain right now. So we are perturbing the brain directly. So when you perturb, then because the motor command is directly perturbed, of course it fluctuates, but after you perturb, after stopping this manual perturbation, it goes back to the original time orbit. So basically the embedded closed loop control is robust. Yes, and also how does this octopus arm store memory? And this is, I mean, very intuitive, but I think this is very important. So as I said, this readout is static. So there's no memory at this, the readout part. We only check the current, so we embed bending sensors inside. It means that we can only understand the current posture of this body. By checking the current posture of the body, can we infer what was happening as an input? So input is a motor command, left or right. And for example, when you check this posture, we can infer what was happening previously in the motor command, right? Obviously, because we have this physical system, it has some physical constraint. So if this arm was bending like this, then of course your motor was coming from here to here. So only by checking this current posture, you can infer back what was happening in the input part. That's how this system stores memory of the previous input. So if you have this kind of posture, then obviously because it has bend here, and this bend propagates with a finite velocity from base to the tip, it stores memory like this. So obviously it's like this. And in this case, because we have 3 bands, we can estimate that the input was injected like this. And this is very special property. So for these soft robots, so if you have some kind of rigid body, then this kind of memory does not happen, right? It doesn't bend like this. So there's a very much special way to store memory into the body. That's an interesting point. Yes, and there are lots of physical reservoirs proposed worldwide recently. And this one, liquid brain, is the world's first physical reservoir. And I think that this, it's called water in a bucket. And I think this paper was published in European Conference of Artificial Life, and in 2003. And this one is the world's first physical reservoir. It's called liquid brain. And there's a attempt using this real cultured neural network as a reservoir. And we are also developing many reservoirs. So not only our team, but in NASA, they use tensegrity. Or we, with the Zurich team, we were working on these quadruped robots. And in US, there's origami robots embedding this closed loop control. And in neuromorphic device science, the physical reservoir computing is now a hot topic. So as you can imagine, by using photonic reservoir, so photonic reservoir means using laser dynamics to emulate those echo state networks. So you can embed extremely high speed recurrent neural network by using photonic reservoir. Or there's an immaterial reservoir approach. So you can use this nanomaterial. So you can make very cheap machine learning network by using this technique. And also there's a spintronics reservoir. So there are lots of types of spintronics. For example, in our team, we are working on these spin torque oscillators. And by using these spin torque oscillators, of course, you can embed extremely high speed reservoir computing. And also recently, it is found, many researchers are now focusing on the robustness against these radioactive environments. So when we bring our conventional PC to the radioactive environment, then it breaks down immediately. But if you use this spintronics, it's robust. It's found to be robust against this radioactive environment. So by using this physical property, even if you are emulating the same function f, the usability is different according to the choice of physics that you use. And for the quantum reservoir, we can embed some kind of quantum task. And recently in IBM Q system, there are several teams working on this quantum reservoir. So the real physical implementation is also now working. Yes, and recently, last year, this was on the web news, but brain organoid reservoir computing was also proposed. So they use this brain organoid as a reservoir. And what is interesting here is because it emulates the entire structure of the brain somehow, minimal brain, it can use this network topology of the real brain. And also it has some plasticity inside. So they show that they can use this plasticity property of the real brain, and it actually contributes to the task performance. Yes, and there are lots of different types of reservoir. Recently, we showed that this unicellular organism called tetrahymena can be also used as a reservoir. So, for example, tetrahymena is just, what should I say, unicellular organism. But by using this system, by using this population dynamics, we injected this population dynamics of the fish, flat fish, of some kind of pond. And because this is a collaboration work with ecologists, so we have this kind of data. So we injected this kind of data to this tetrahymena reservoir and try to emulate predict the future dynamics, population dynamics of the flat fish in that pond. We can do this kind of things. Okay. So anyway, there are lots of physical reservoirs worldwide recently. And actually, in this stage, so for example, photonic reservoir, spintronics reservoir, there's lots of procedures or scheme established. But for example, for these tetrahymena or these kind of a bit exotic dynamics has lots of challenges. And we are now thinking how to increase the computational power of these reservoirs. So there are lots of small reservoirs, and they argue that if this reservoir becomes big, we can outperform the current machine learning network. But of course, we can wait for that. But right now, it's okay to have some kind of scheme right now to make these physical reservoir function similarly to the current machine learning network. So one very straightforward way is to assemble these small guys and construct the big network. And this is called higher order reservoir computing. And the special case, the feed-forwardly connected physical reservoir is called physical deep reservoir computing. And so the computational node is increased. So simply the capacity is increased. So of course this direction is promising. And there are lots of techniques to tune these weights. So because these physical reservoirs are connected with the linear weights, it means that we can somehow tune these linear weights because this linear weights is not inside the physical dynamics. And so there are several directions. Like if you have the very precise physical model, then you can calculate the gradient of your entire system. So you can tune these weights. But usually, of course, there are several teams working on that, and that's okay. But usually, there exists real problem. So you cannot use that directly to the real physical system. And another team is working on this, making some surrogate model for each physical reservoir. So by using this surrogate model, you can make that system differentiable. So you can obtain gradient. So you can tune these physical parameters or these linear weights. But that also has some symmetrical problem. And recently we proposed the gradient-free approach, which is called augmented direct feedback alignment. And this approach does not require the gradient. So we don't need any precise modeling of the physical reservoir. But unfortunately, right now, we are still working on why this. So we found that this works. So usually, when you do some back propagation approach, you need to have the derivative of your system. And obtaining derivative means you have the good model of your physical system. But this one is very hard to obtain in the real physical systems. And we found that we can replace this derivative with any nonlinear function g. And applying this nonlinear function g, actually the back propagation successfully works. And we are now checking why this works. And there's certainly there exists some kind of condition. And yes, we are now checking what is fundamentally important to make this augmented DFA work. That's what we are thinking. And so, as I said, this direction is promising. However, for our team, there's several uncool points here. So as I said, these linear weights are right now, it's not embedded inside the physical dynamics. So today I would like to propose our recent attempt to use the real physical dynamics itself as a deep neural network. It freezed. Wait, sorry. Okay, so yes, so to understand our approach, recent approach, I would like to dig deeply into this question: which dynamics is good for which kind of computation? And as you guys already know, there is an important property called echo state property, which is proposed by Herbert Yeager, and this is very important. So basically, what we are doing in recurrent neural network is that we want to emulate this kind of function g, which takes previous input. This is a task of recurrent neural network. And what we are doing in reservoir computing is that we have this kind of input-driven dynamical system. And by adjusting this readout part with some kind of function psi, this can be linear or non-linear. And we try to emulate this G, right? And for example, when we think about using physical dynamics as a computational substrate, because as we know, dynamical systems behavior depends on the initial condition. It may happen that the response of your system depends on the timing that you inject the input, right? This really avoids the reproducible response of your system because it depends on the timing. But if your system has echo state property, we can avoid this kind of problem. So this echo state network, echo state property suggests that, this one is more obvious. So you prepare your reservoir and you run your reservoir from different initial condition. And then you inject your input stream, then the response starts to synchronize. It means that your system, your reservoir state is only the function of the previous input only. So it forgets about the initial condition, conditions dependency. So there's no dependency with the initial condition. So this is the important property of the the reservoir to make your reservoir successful. And this can be characterized by this common signal induced synchronization. And also when you measure this conditional Lyapunov exponent of this system, this shows negative value. You can characterize so if you have those physical reservoir, and if you measure this common signal induced synchronization, or if you measure this conditional Lyapunov exponent, you can check whether your system has echo state property or not. And this is very important. And yes, and also this one is a bit different from the echo state property, but the interesting point of the reservoir computing is that, so as we discussed, our task is to emulate this kind of nonlinear function G, right? Then, for example, if we have shift resistor, and if we have some function G, function that we can emulate G, so if you have some universal approximation property readout, then you can emulate G, for example. Then you can emulate this kind of function easily. But the interesting point of reservoir computing is that we don't need this kind of sophisticated architecture. It is found that if you prepare this kind of random neural network, you can emulate this kind of thing. So we don't need this kind of module inside your network. This is interesting. And to guarantee this property, you need to have echo state property. That's the interesting point. And let's check more into detail. So let's see the very simple case, one-dimensional linear example. So uppercase, we have this kind of very simple reservoir, and you inject your reservoir, one-dimensional reservoir, with these input trees. Then if you wait for sufficiently long time, as you can see, the dependence of the initial condition, because this part is contracting, this disappears, this term disappears. So you can see that your reservoir state is only a function of previous input trees, right? So this is obviously your state is only a function of previous input. This is called echo function. On the other hand, in this case, for example, if you have this reservoir state, and if you just write down each step, then the dependence of the initial condition is still there. So it means that your state, reservoir state, is not only the function of previous input, but it has the dependency of the initial condition and also the time. So there exists the timing issue. It's not reproducible at all. So this means that usually the chaotic dynamics that we observe in the physical system or limit cycles cannot be used as a reservoir directly. And of course, there are lots of attempts. But so if we summarize from this echo state property viewpoint, it's very important classification can be done. So this one is the conventional echo state network that is successful echo state network, which has echo state property. So you can describe your system, your reservoir state only by the previous input trees. Second case is your reservoir state can be described by this input plus the initial condition of your state. So it means that even if you're injecting the input externally, still there is some kind of effect of its own dynamics inside. So it's not completely synchronized with your input. And third case is you have input, but also some unknown input. We call this noise. So we also have, and it also have the effect of its own. So its own dynamics is also like a noise, right? So we have this kind of three conditions, and we basically think that this is successful, and these guys are not successful. But of course, there are several attempts to make to use these unsuccessful reservoirs for a computation resource. And our team is also working on that, but let's see step by step. So, okay, then is octopus arm really has a coset property? So I have checked that. Then, as you can see, so this one, I'm checking the common input-induced synchronization. So input sees is the identical, but you start your system from different initial condition. And we change the environmental condition. You vibrate your system in the air. Then even if you inject your system with the identical input, it won't synchronize at all. However, if you use tap water environment, as we saw in the first slide, as you can see, it shows a nice synchronization. But the two videos now overlapped right now. As you can see, this one is not synchronized, but this one is synchronized. So we can say that our octopus arm only works in the water environment. If you vibrate that in the air, although it seems very complicated dynamics, it does not have the reliable computation. We can, please check this paper for details. And also in echo state network, we also can check what is happening. So we all know these settings, so I won't go into detail. The important point is we have this spectral radius as a hyperparameter. And also this time, this scaling of the input weight is also very important. And also, probably you guys already know that there's a measure called Lyapunov exponent, of course, and it can characterize how this small perturbation expands exponentially. And if this measure was positive, it means that your system is chaotic. And if it's negative, then it's not chaotic. And later, we will use this measure to analyze the conventional deep neural network. But anyway, if this value was positive, and we check this finite time Lyapunov exponent or local, so we can see that this one is, we call this local Lyapunov exponent, and this is a time average. And usually, so we have this finite time Lyapunov exponent, and also these, this one is one-dimensional case, but for example, in the n-dimensional case, we have n Lyapunov exponent, we have a Lyapunov spectrum, and we just pick up the largest Lyapunov exponent. And if this one was positive, we call this chaotic dynamics. And by analyzing this, and in this case, we call this conditional Lyapunov exponent, and we're only checking conditional largest Lyapunov exponent here, because we have input right now. But anyway, if this was positive, it is chaos. It shows chaos. So there's no echo state property. Okay, now we have spectral radius. And this section is very important, very famous. So we fix the input scaling and then changing this spectral radius. Then we observe some bifurcation from order to chaos around this spectral radius 1. If the input scaling is small. But if you increase this input scaling, then this boundary is somehow showing this kind of curve. It means that if you prepare your reservoir in the chaotic regime, but if you change your input scaling, then still you can improve the equal state property of your system by using this input-driven bifurcation. So even if your system was set as chaotic, by tuning this input strength, you can suppress the chaos and improve the equal state property. But anyway, this part is left behind. It says that we cannot use this region. But I want to use this part. So we are now thinking many approaches to use this left behind part because we observe many chaotic dynamics in the physical reservoir. So I want to use that. So yeah, there are lots of approaches to use chaotic dynamics. For example, forced learning is very famous. So usually as we saw in this case, if you control this input strength, you can suppress the chaoticity in the reservoir. They are using this approach. So when you inject input A, you want to obtain this corresponding attractor A. When you inject B, corresponding attractor B. When you inject C, then corresponding attractor C. And this part is not because it's reservoir computer. We don't tune this part, but we only tune this readout part. And then, as you can see here, if you don't put inject input, then it has its original chaotic dynamics. When you inject the input, it goes to the corresponding attractor immediately. We can do these kind of things very quickly by using this intrinsic chaos. So 1 hour. So we still have 20 minutes. So 50 minutes. 10 minutes, okay. Okay. And this kind of phenomena can also observed in the, for example, in the physical reservoir called, for example, spintronics. And we found that, for example, when you tune this input amplitude, then, so spintronic oscillator is usually a limit cycle, showing a limit cycle. So if you inject a very small input, you cannot use that because it doesn't have equal set property. But if you inject a strong input, then you can induce input-driven bifurcation, and you can improve its equal set property. So for example, this is so when you increase the input magnitude, at first it doesn't have, it's a limit cycle, but step by step, it shows bifurcation. So at first it's order, and then input-driven chaos, and again order. So by tuning this input magnitude, by inducing bifurcation, you can improve equal set property of the system. That's one way to use. So even if you have chaotic reservoir, by tuning the input strength, so using this bifurcation phenomena, sometimes we can improve that reservoir to be usable for your purpose. But that's something that you use, you somehow suppress your chaoticity of the reservoir. But today I would like to introduce our recent, this is not published yet, it's in archive, but I want to introduce this approach. So we can use this natural chaotic dynamics as the deep feed for neural network. So at first, I want to start from this point. So recently, this large language model is very popular. And around 2020, we were also focusing on this system, BOT. And right now, it's GPT-4, but at that time, maybe it's like a GPT-2 or something. It's very earlier age. And the system size was not so big like currently, but we were focusing on this activity of BOT or GPT-2. And we were interested in what is happening inside the network. And actually, there are lots of types of BOT, and we focus on the recurrent neural network type BOT, which is called RBOT. And RBOT iterates this transformers encoder part. And then by using this corpus data, they tune, by using backpropagation, they tune these inside weights. And it works as a large language model. And because this is recurrent neural network, we analyze what is happening inside this internal dynamics. And we found that there exists chaotic dynamics inside. And also what is more interesting is that when you iterate this system for a very much long time, then it goes to some periodic orbit. So actually this one is so this Albert includes this transient chaos. So it shows chaotic dynamics only in the transient phase, and then it goes to the periodic. But anyway, we found some kind of chaoticity inside the large language model. So we thought that maybe chaos can be usable for deep neural network. And our working hypothesis was like this. So at first, let's think about Danko system as feed-forward neural network. So you have this discrete time Danko system, and each time step, it means that the time step direction is you increase the layer. So you think that one time step is one layer. And then in this case, you inject some input as an initial, so initial condition is the input to the initial layer, and you just iterate this system. And we think that this is a working hypothesis, but for example, if your system was not chaotic, if it has fixed point attractor, then even if your input data was different, for example, if this system should be classified into different class, if you inject these two input, if you have fixed point attractor, then basically these two input goes to the global attractor. So we cannot, what should I say, take out the input important information. All the information is lost. But if your system has chaoticity, or if your system does not have a coset property, then by definition, your system should have the memory of the initial condition, right? So maybe this property is important, we thought. So we made this kind of model called feed-forward echo-state network. So we have input, and we have this internal dynamics. It's just an echo-state network. And we just, as an input, we just tune this W in and W out by using back propagation. And you just inject this input as an initial condition of this echo-state network. And then you run your echo-state network for T time steps. This is a layer. And then you use this final time steps as a final layer. And then you apply this W out and obtain your output. This is the system. And we found that it actually works. It works if it is chaotic. So you have this, so this is the MNIST classification task. You have this input data. You inject this input data to the non-chaotic echo-state network. Then as I explained, because it has global fixed point, all the data goes to the fixed point, and it's very difficult to take out the important information from the dynamics. However, if you use chaotic dynamics, then separation is enhanced. So classification is enhanced. That's what we found. And interestingly, so as I explained, so this is echo-state network, and by changing the spectral radius, we can understand the dynamical phase of that system. And if the system has less spectral radius than 1, this is the region that echo-state property works fulfilled. But as you can see, so please check that. So this, if the color was bright, the performance of the MNIST classification task is high. And if this color was dark, then the performance is low. As you can see, the region which fulfills echo-state property, it shows very low performance. And this is iteration time. It means the number of layers. And this is understandable because if you iterate several times, then it goes to the global attractor. However, in the chaotic region, it works. And also there exists some kind of interesting appropriate number of layers, which was characterized by Lyapunov time. So because Lyapunov time characterizes so the small tiny distance spreads over the state space. So it becomes entirely unpredictable if you go out from this Lyapunov time. But when within this Lyapunov time, this small tiny distance has some kind of predictability, although it is chaos. So it is using expansion property of the chaos, but it's still using some kind of correlation. And if it exceeds this Lyapunov time, then the computation power is reduced. And we also found that around this Lyapunov time range, the convergence time is very quick. So it converges. The learning is very fast. Okay, so because we checked that in the conventional echo-state network, we checked whether our hypothesis works for this spintronics dynamics. And as I explained, this spintronics, especially for this time, coupled spin-torque oscillators shows chaotic dynamics. So it's a simulation, but we checked whether this chaotic dynamics of coupled spin-torque oscillators can be used as a deep neural network. And we found that it also works. So in this case, as I explained, this spin-torque oscillator starts from the limit cycle. So it doesn't have those fixed points. So it starts from limit cycle. And when you increase the coupling magnitude, it becomes chaotic. And basically, all the region works as a deep neural network. Yes, and if the coupling magnitude was too strong, then in some region, this is also related to the Lyapunov time, we think, but we are not measuring that right now. But in some region, there's some region that does not work. And we can use this architecture by combining with several conventional work, like we prepared some one layer convolution layer, and then assembled with this coupled STO having chaotic dynamics. Then it showed this kind of 99% performance of this MNIST task. So somehow we achieved this, what should I say, state-of-the-art machine learning network performance by using spin-torque oscillators. So in our approach, chaotic dynamics has a potential to be used. Okay, thank you very much. And I would like to acknowledge all the collaborators, lab members, and RC seminar members. Thank you very much.